and see the types of topics which we shall be considering. We have arranged this entire course in 7 or 8 sessions to start with, where we just want to see which topics we shall be covering in the entire coursework. The first lecture that we shall be considering today is the primary objective of structural engineering activity, basic classification of structures, building blocks of structures, then the materials that we consider in our field, then the loads that we apply on the structure, the tools of analysis, and some demo if required using the software which is very popular, ETABS and so on. I think most of you are exposed to the software ETABS or STAD or something. Okay. Now this is the outline of our lecture today. In the next lecture we shall be reviewing what we studied in the first lecture. Then we shall be considering the theories in strength of materials, how we calculate stresses and so on, the assumptions made in various theories, because you determine forces, then the stresses, and then your design starts. So the governing equations of strength of materials will be studied, basic formulae which we use to convert forces into stresses will be studied, and in some demo using either ETABS or STAT. In lecture 3 we shall be considering the real structures which we shall be analyzing, which may be determinate or indeterminate. Then basic principles of structural analysis we shall be seeing. Then the fundamental methods of analysis we shall have a look at that. While computer based matrix methods we shall just see outline, because we will not be going into the actual working of the method, that's not required. You have got very powerful tools and the softwares. In lecture 4 we shall be considering the design part. So far we were first 3 lectures were only analysis based. We shall be considering the design, where we shall consider the theories involved in the design, the working stress method, the ultimate stress, and the limit state method. Then the design for individual forces we shall see, that a member carrying axial force or shear or bending, how they are designed. And then when you have got actual member with combined forces, we shall be considering those elements design. Later on in lecture 5 we shall be considering the actual structural element as such, like design of beams or design of slabs, how we do it. Otherwise it is only element so far, element design, either design a beam or design a slab with given data and so on. Then we shall consider the important aspects of design process, how to determine the moment of resistance of a given section, the determining the stresses in the beams, and design the section to resist the given moment. So we shall see some important aspects of this design process. Then we shall consider the design of columns as such, the axially loaded columns under axial load and moment, biaxial load, and so on. Then we shall consider the design of shear walls in isolation, then design of footings, isolated footings, and so on and so on. Later on we will consider more complex types of structures like the raft foundation, how to design that, or the pile foundation, design of pile caps, and so on. And lastly, if time permits and if you all have enough patience, we shall be considering these important topics which are more complex in nature, the real structures, that is design of water tanks, design of retaining walls, folded plates, long span structures, the bunkers and silos which we use for storage purpose, and you have got cylindrical shells, roof types of structures, and lastly the topic in which you are mostly interested is the pre-stressed concrete. Okay. So this is the outline of our total 9 lectures which we have planned, and hope that it will finally enlighten you to the extent required in this particular case. Now we shall consider today's presentation, that is structural engineering, an overview and basic concepts. In this particular lecture, the topics which I have planned to cover So there are these topics to be covered. The primary objective of structural engineering, with which we start with this subject. Then the basic classifications of structures. Then we have the building blocks of the structure, which finally make a full-fledged structure. different materials which we use, their properties, their, you can say, the uh, important properties which are used in the analysis and design, and so on. Then the loads on the structure, different types which we have to consider. Then we shall consider the tools of analysis, and with that we will close the lecture for today. So our idea is to get an overview of the field in which we shall be considering the entire presentation. The primary objective that we see in structural engineering is to plan, design and detail a structural system which will carry safely the loads coming on it. So someone says that, okay, you design this structure. The planning of structure is different aspect, but we say that someone gives us a structural system. Okay, this is the building of this height and column locations and all that. Then we say that, okay, we have to design this structure to carry certain loads. So loads are also specified, and we say that design the structure in such a way that the load is carried safely. Okay, that is what we expect from the design that you consider over here. So we say that we start with a structural system. Now when you say that you have got a structure, so we have to just see as a engineer what you call a structure. So a common man, if you ask a common man what he understands by a structure, so a common man will look at the building and say, oh, that's a structure. Or he will look at a bridge and say that that is one more type of structure. Or maybe containers are there, or water tanks, so he will say, oh, that's also a structure. Sometimes you can see the retaining walls which are presented near the approaches to bridges, or when the hilly area is there. Then you have got dams, massive structures which are also having certain purpose for retaining the water and so on and so forth. So those are huge structure. A common man will understand, oh, that is a kind of structure. Or an aircraft. If you see, aircraft carries huge mass inside it. It has to safely fly, and then several forces are applied on it, and there is apparently no support, as we see as a layman, that it is just moving in air. So there is no firm support as we consider for foundation of our buildings and so on. But there are fixed points where the entire load is finally resisted in terms of that air blast that is finally driving it forward and lifting it up. So those fixed locations are provided in the aircraft at which the whole mass is resisted, or the gravity forces are resisted. Then we have got the ship which are floating on water. So they are also massive structures. They are uniformly supported through the buoyancy, and someone has to design that as a structural engineer. Then we have got these automobiles, then you have got tunnel structure. So where the whole heel is cut, and then you have got the passage going through it. So you have to design it, the tunnel lining and so on, for the load coming from the top and so on and so forth. Then we have got the jetties which are there in the harbor where the ship hit it, and then ship are berthed there and so on. Then you have got cranes, you have got balloons which are used for various applications. So someone has to design the structural aspect of these floating structures and design. So as a layman, various objects are seen as structure. That is as far as a layman is concerned. But apart from calling it as structure, a common man doesn't understand more than that. It is not expected from. But as an engineer, you will look at the structure in a different way. So if it is a beam where you understand that it generally carries some lateral load and supported and so on and so forth. So if it is a beam, then you will say, yes, that's a kind of structure. You have got columns which carry certain specific type of load. You have got arches, so you will say that yes, arch is a kind of structure which you will understand its behavior, and you know various methods of its analysis. There are the cable structures, so cable stayed bridge. Now I think your company is doing a lot of work in that. So there are those cables which are, or even suspension bridges are there where cables carry a lot of load from the bridge. Then there are trusses which you see at various locations, industrial roofing, or on the bridges in the railway platform. So those trusses are provided. They may be plain trusses or space trusses. Then you have got the frames type of structures where you have got slightly different behavior than the trusses, where you have got rigid joints and various types of forces are expected in it. While you have got floor grid system, which also you have seen that it is a kind of structure where the whole structure is in one plane and you are applying it load perpendicular to that. Then you have got slab as a continuous structure, Then you have got shells, curved structure that you come across for roofing or various other applications. Then you have got folded plates, which also you see in many applications, roofing type structures. Then you have got three-dimensional solids are also used, like foundation blocks or massive foundation blocks used for supporting generators or compressors. So huge foundation blocks are provided for supporting the static load as well as some dynamic load coming there, and so on. Then you have got plane stress problem, like our beam is a kind of plane stress problem, which we shall see in detail later. Plane strain is another type of structure where you consider, for example, a dam which has got huge length. So what you do is you cut a slice, and for that slice only you do the analysis and presume that the whole thing is valid for the entire length. Like your retaining wall has got huge length, but you take a slice 1 meter length and then analyze it for that 1 meter and then say that the same thing is valid. So if your structure is enormously long in one direction, then we don't worry about that direction. We only take a slice in one plane, analyze it, and then say that it is valid for entire. Same thing happens is true for tunnel. The tunnel is long, kilometers in length, but we take a slice, and for that slice you analyze it and then say that it is valid for whole length, like that. So on the same line you have got axisymmetric shell, like cylindrical shells, or you can say those cylindrical containers which are symmetric about their longitudinal axis. So there are various types of structures. So as soon as you see these types of entities, then you develop in your mind some idea as an engineer, and then you say that okay, if this is the kind of structure, then you also expect what kinds of forces may be there, what kinds of displacements are expected there, and so on and so forth. So for an engineer, a structure carries different meaning. For a common man, the broad outline is different, while for an engineer, we don't just say building is a structure, but we immediately say, oh, is it a plane frame or a space frame, or is it a truss, and things like that. So for us, for some additional information is required rather than a vague description over there. If someone says only bridge, then you don't understand much about that. But if you say, oh, it's a cable stayed bridge, then something is more clear to you. Or if it is only a pre-stressed concrete bridge with girders and so on, box type, so then you get a certain idea about the behavior of that structure and so on. Okay, so we say that once you say you have got a structure, okay, then we say that a structure as an entire entity is made up of certain elements. So we say that a structure is an assembly of different members or elements suitably connected to each other and supported in such a way that the loads coming on it are safely resisted and finally transferred to the foundation. Okay, so we have got a structure like a truss. A truss is made up of all those different members which are suitably connected. So we say that we have got a suitably connected set of elements which are connected either by a pin joint or by rigid joints and so on. They are somehow connected and they finally are subjected to some loads which are to be resisted by those elements, and then finally it is transferred to the foundation. So we say that every structure has got some building blocks out of which the structure is made. So you have got those, like for trusses, so you have got various members, they are connected, joined, and then you have got the whole truss. So truss has got those building blocks and so on. So we say that every structure has got building blocks, and those building blocks have got certain characteristics. Okay, so we say that we have got certain building blocks like a truss. If you consider a truss, for example, then we say that for a truss, okay, these are very elementary concepts, you have studied that many times. So if you consider this truss, for example, then we say that we have got this simple truss. I think there is some problem. Okay, so we'll say that you have got this truss element. Sorry, truss. If you consider. नॉर्मली चालतं ते, पण आता आज काय झालं बघायला पाहिजे.
चार्जिंग वगैरे नसतं ना आपल्याला?
नाही त्याच्यात now it's working. Okay, Swapnil झालं रे. So if you consider, for example, a simple truss. झालं. So you have got these various members which are finally provided in a truss. So you have got all trusses are made up of these simple members, and if you consider individual member, then we expect for this truss to carry only axial force, which may be either tension or compression. So as soon as someone says, oh, you have got a truss structure, then you expect that its building blocks are simple members connected to each other by theoretically a pin support, though in reality we will have welded connections and so on. But as a concept we will say that they are connected in such a way that finally every member either carries a compressive force or maybe a tensile force. Okay, so that is all we expect for a truss member. So as soon as you analyze a structure which is a truss, then you primarily expect that yes, all its member would carry finally only the axial forces, tension or compression. Similarly, if you consider a beam element, then for a beam we say that on the same lines we have got a beam which is suitably supported over there. Okay. So we have got a simple beam which is simply supported, okay, and there are some loads applied on it. So we say that for a beam at any section we expect that there will be some shear force and there may be some bending moment. That's all. If it is a simple beam, plain beam in one plane and so on, so it will carry only shear force and bending moment. We generally don't expect axial force in the beam, though when you consider a three-dimensional structure, all other types of forces are also present. Similarly, if you consider a plane frame, for example, for the plane frame that you have there in the situation, then we say that for the given plane frame, it is a two-dimensional structure like a simple plane frame that you come across in considering the situation. So you have got a simple plane frame which may be fixed base and so on, subjected to some loads applied at various locations. Then we say that individual members of a plane frame would carry the axial force, would carry the shear force, and may also carry bending moment if it is a plane frame. If it is a cable element, then we expect it to carry only axial force, which is tension. It is a tension only element, and it will be thereby subjected to only internal tensile force. If it's an arch, then we expect it to carry all three forces like a plane frame, axial force, shear force, bending moment, and so on. If you consider a continuum structure like a slab, for example, then we say that for a slab type of structure, for a slab structure where you have got, for example, the whole slab lying in a horizontal plane, for example, and is supported all along, okay, supported on all edges by providing beams and so on, then we say that for an arch, for a slab like this, the individual slab will bend in this direction also. So it will bend in this direction as well as it will bend in other direction also. So we expect the individual elements or individual building block to contain bending moment in x direction or bending moment in y direction, and there will be shear force also because the lateral load is to be resisted at the support. So we expect for a slab to carry bending moment, shear force. The bending moment can be in one direction or in other direction, It is also subjected to some torsional movement at the corners because the bending moment is changing all along. So at some point you have got both the moments present and they develop a torsional moment there. So we have got the bending moment, the torsional moment and the shear force in a element in a slab. Similarly, you have got this plane stress element which I have indicated to you. You have got a beam which is generally classified as a plane stress element. So you have got a beam. So I have got a beam. I am just showing it in an exaggerated fashion. Whatever its depth, so it is suitably supported, say hinge and roller, and that is the depth of the beam. So we say that for the beam which is having a small width, the width is very small. Many times we come across beams say 200 by 800 or something like that. So if it bends, then we say that the whole beam remains in one plane. It may bend in this fashion. Okay. So it will bend in this fashion and like that. So all the points remain in the same plane. They get displaced either vertically or horizontally in that fashion. So it has got only two types of displacements, the vertical and horizontal if it is in vertical plane. And it will develop the internal stresses, like it has got an axial force, tension or compression depending upon whether it is above the neutral axis or below the neutral axis. So it will have tensile stresses or compressive, and there will be shear stress also. So it has got three types of stresses which are shown over here: sigma x, sigma y and tau xy. So these are your plane stress elements where it takes axial force sigma x, direct vertical stress also it will have due to the load, and there will be a shear stress at the cross section. Okay, so this is the type of stress that we expect in plane stress element like a beam. If you consider plane strain element, plane strain is a typical retaining wall or the dam or the tunnel that you see. So there it has got enormous length, there is a cross section. So we analyze the cross section, but it is different than beam. For beam the thickness is very small. Here for that cross section the thickness is in kilometers because it has got huge length. So we have to consider some interaction between the adjacent elements. That is many times not very significant, but as a behavior we say that it has got in its own plane in the cross section, it has got sigma x, sigma y, that is in plane stresses. It has got shear also in the plane, and for out of plane it has got that stress called as sigma z. So for plane strain element like part of a tunnel or a retaining wall, where many times we don't bother about retaining wall, its plane behavior only is considered, and for that plane behavior we say whatever is the bending moment or the shear, that is all we consider, and so. Then there are membrane elements like thin membrane that you consider. You must have seen at many places fabric structures. So those fabric structures are used for roofing purpose. So they carry only tensile forces in both directions. So many times you come across such types of elements which are good for only one type of resisting one type of stress, like your cable. It can take only tension, nothing more than that. Similarly, you have got shell structures like the cylindrical roof shell that you consider, where it takes in plane forces like Nx, Ny or Nxy. So if you consider, for example, a cylindrical roof, for example, you have got a huge cylindrical roof which is suitably supported. At this place it is supported, at the other end it is supported, while along the edge many times some beams are provided, edge beams are provided over here. Okay. So it has got supports at these two opposite ends. So if you consider any element of this particular shell, then it has got in plane forces like Nx, Ny. So those in plane forces are shown over here, Nx, Ny. There is in plane shear also like this. So this Nxy. Then you have got out of plane shear Qx and Qy. Then you have got Mx, My, Mxy. Moments are also there depending upon the type of load that you are considering, and so. And it is just to indicate the kind of behavior we expect from these different types of structures. And then you have got solid element, like as I told you, that machine foundation block. So those huge blocks are provided which has to carry the weight and the dynamic nature of the force and so on. So all those forces, and it is supported on soil. So those soil reactions are also there. all of that put together gives it finally for any element of that foundation block. So you have got a huge foundation block that I am showing over here. So it is a huge foundation block which may be partly embedded inside the soil. So it is all embedded, and you have got some equipment mounted on it, which may be a rotating equipment like a compressor or a generator and so on. So it is all subjected to certain loads, and it is supported only on the soil which is in contact with the foundation all along. So any 3D element, if you take for this particular foundation block, then it is subjected to normal stresses sigma x, sigma y, sigma z, and the shearing stresses and so on and so on. So we say that for every element of a structure, as soon as an engineer you understand that it is this type of structure, then you immediately realize that what kind of forces are expected in it. And then when you do the analysis, then you come across the results, and then finally you realize, oh yes, these stresses are expected, primarily these will be the stresses present, and so on and so forth. That is as far as the internal forces are concerned. In addition to that, we have got the structure deforming in some way. So for a plain truss, when we say that okay, it is subjected to some loads, some internal forces are developed, then there are some displacements occurring in the given structure. So for a truss element, we will say that okay, if it is a plain truss, then it will get deformed, and in the deformed state, for example, you have got a plain truss and subjected to some loads, okay, and let us say supported in some way, okay. So we say that at any point it will have, if you consider its deformation, then it will have either a horizontal deformation or a vertical deformation. So if it is a plain truss, then we will say that it will have delta x or delta y as the deformation. If you consider the beam on the same lines, then we say that for a beam, when you consider the behavior under the influence of some loads, then we expect the beam to deform in this fashion, and then at any point we say that it has undergone downward deformation and it has undergone some rotation also. While originally it was a straight line, now it has undergone some rotation. So it has undergone two types of displacements. The downward displacement, if you consider the conventional beam, and then rotation. These all internal forces will finally give us the behavior of the structure. Similarly, for the plane frame or a space frame, we consider that it is undergoing some deformations over here. So if you have got a plane frame subjected to some loads, then we say that it is undergoing a displacement in this direction, it may undergo a displacement in this direction, and it may undergo a rotation like this. So we say that it has got these three characteristics for deformation. Internal forces may be axial force, shear force, moment, while the deformations will be delta x, delta y, and the rotation. Similarly, we say that for any structure that you consider, for example, for the slab, then we say that on the same line it has got deformation out of plane, it has got rotation in one direction, rotation in the other direction, and so on. So for a slab on the same line, we say that it has got theta x, theta y basic rotations, and delta z, assuming that slab is in one plane. So you have got slab which is in one plane and subjected to lateral load. So it will undergo rotation like this, and the downward displacement like this. So we say that at any point in the slab, we will have three displacements. In the sense, two will be rotational displacement and one will be linear displacement like that. In the same lines, we say that for every structural element or structure that we consider, there are fixed behavioral characteristics that under the influence of normal loads, it will undergo such types of deformations and such types of internal forces will be developed. So when you consider the analysis of the structure, then we say that for the analysis of the structure, we realize, okay, we expect these types of deformations, these types of internal forces, and so on and so forth. Okay, so we say that we have got a structure which is having some building blocks. These building blocks have some characteristics in terms of internal forces, and structure as a whole will undergo some deformations, which is also characteristic of the structure. Like a truss, plain truss will have its own deformation, delta x, delta y. A beam will have rotation and displacements and so on. So as soon as you classify a structure, then you immediately bind it with two characteristics: what internal forces are expected and what deformations are expected in them. Okay, now that is what we say, that the engineer will understand the structure in this fashion. Okay, so we have got various types of structural elements, and they develop all types of deformations and forces. With all that, you might get confused over how many things I should remember. But no need to do that. We will say that having seen all of that, now we say let us summarize what is it. Then we say that okay, there are only 4 types of forces. Fortunately, structures may be, for a common man, millions of types of structures are. For engineer, 15, 20, 30 types of structures, because it is only building blocks with which you are. But internal forces, now you have got only 4 types. The axial force, which may be tension or compression. Then you have got shear force. So shear force may be, so if you take this as a beam, it may have a shear force like this, vertical, or it may have shear force like that. Okay, so different types of shear forces may be there. Then you have got bending moment. Again, for the same member, it will bend in this plane, so there may be bending, or it may bend like that. Okay, horizontal plane also it may bend, so it will have 2 bending moments, and that is all. And lastly, we have got torsional movement. So torsion is different. It is to undergo a torsion like this. So when you twist it in this fashion, okay, that is a kind of movement developed. So we say that no matter what structure you consider, you have to determine only 4 types of forces: the axial force, the shear force, the bending moment, and the torsional moment. So as far as our objective is concerned, we will say that once you see the analysis will consider these forces. Okay. Having seen 4 types of forces, we will see what types of stresses are developed, because force alone is not going to give you proper information about the design. For design purpose, you need to know the stress, because later on we will see that every material has got some characteristic, how much stress it can carry. That is the strength it has got. Like your M20 concrete or your steel that you consider. So you say it is Fe or Fy 250 grade. So it has got yield stress of 250 MPa. Okay. So that is the stress that we consider. So if you get information or there is some member and it is carrying 30-ton load, is it safe? You can't decide that, because unless you know the stress, so you should know what is the force per unit area, then only you can say, oh, because your guiding factor is the stress, not the force. Force may be anything, but you provide some area and then now you know what is the area provided, so you can convert force into stress and then finally say, oh yes, it is within limit or not. So there is a permissible stress, later on we will see, and there is an actual stress, and then on comparing the two, you can realize whether it is a safe structure or not. So we say that finally we have to convert even the forces into stress. So we have started with all different types of structures, different types of forces, but shortlisted to only 4, and from 4 forces, now we say that as far as stresses are concerned, only 2, but we still say it is 3, because a tensile and compressive, they are both axial stresses, normal stresses as we say, but their behavior is sometimes different. The material properties are different. Sometimes in tension it might carry some stress maximum, or compression it might have different characteristics. So we classify tension and compression separately, because their properties for different materials are different, but it is a normal stress nevertheless. And lastly you have got the shear stress. So shear stress also has got a peculiar permissible value for any material. So having considered all types of structures, all types of forces, we convert them into 2 types of stresses: the in plane or the normal stresses, tension or compression, and the shear stress. That's all. The shear again, as we see, it can be in one direction or in other direction and so on, but it is a shear stress nevertheless. So we say that for any structural element that you are considering the analysis, finally you are determining the stresses, and then your design process will start, whether the actual stress is what the material can carry or not. So we say that for any structure, we have got one aspect that you should determine the forces, you should determine the stresses, and then your next item starts as to what material you are going to use. See, as a student, you have seen that problems were very simple now that you see, but as a student, you always realize, oh, they are very complicated because you were not exposed to real problems. So, for student, as you realize, the professor tells you, oh, take this 4-meter span beam, take this cross section, take this load, everything is given. Take this support, oh, that is also given. And take material as concrete, oh, M30 grade, everything is given. And now you design it, how much reinforcement. About reinforcement also he will say use Fe415. So everything is given. And now you have to design. But as a real engineer, now you see, no one gives you such a defined problem. Only people give you a vague problem. Oh, I want to cover this area. Give me something. Give me something. And then the problem is very complicated. You have got so many options. So a lot of time is spent in selecting option. And if you give the client 2-3 options, then he will immediately say, give me the cost of each. Because then you have to do the design and then finally compare. Which means you have to give lot of information in terms of even the material also. You have to ask him whether he will prefer steel structure or concrete or pre-stressed concrete, because user doesn't know what it is. He will say that I want something good, but that good just doesn't mean anything to an engineer. Engineer has got various options. So as far as materials are concerned, you have got many options. So there are natural materials that you come across, there are man-made materials, there are combination materials. You take 2-3 materials together and make something different. Then you have got structural materials, which we shall see. Then you have got aesthetics material, which are only there for the looks and so on. And you have got some functional material. I mean, they have got only some specific objective for which they are used in the given structure and so on. So your natural materials are like your soil or stone or sand or timber, the natural fibers. So like jute or even human hair, they are also used as structural members, structural applications. Then you have got water as a structural member, because when you float object or you have got water to be retained, so you treat water as some material with some characteristics and so on. Then you have got air. When you are using balloons, then you have got air inside as well as outside, and then you have to design the structure for resisting air pressure from inside or from outside and so on. Then you have got human bone, it has to carry some load, so it has also got some characteristics to carry the load. So many times when artificial joints are to be made or to be supplemented in a medical application, then you have to consider the bone with its structural properties. And you have got skin also be used as different applications for membranes, so that also you can use as a structural member. So you have got these natural materials available for various applications. Then you have got man-made materials like bricks or concretes or metals, iron, aluminium and so on. You have got non-metals like carbon, sulfur and so on. They are also used in many applications. Then you have got compounds, chemically bounded compound like water or salt and so on. You have got polymers, plastic or rubber, they are also used in many applications. And man-made fibers like glass fibers or carbon fibers, nylon fibers, they are also used in many applications. So you have got many man-made materials. Then you have got the combination materials, where the materials, where 2 or 3 materials are either physically or chemically combined, and then you get some desired properties out of that, like compounds or alloys or composites. Many times different materials are combined together to give the required properties. Then you have got compounds like water or common salt or polymers, where the combination is made by chemical reaction, and then you get a material which is entirely different than its ingredients. So that is a kind of material which we get as compound. Then you have got alloys. Many times we come across high strength alloys in pre-stressed concrete. You have got that very high strength cable material is there. So you have got stainless steel or bronze or brass made up of different elements, or nickel, titanium and aluminum gives us nitrile and so on. So various alloys are also available for different applications. Then you have got composite materials which are having specific characteristics. There is a binding material and there is an ingredient into it. So that like our concrete, so it has got a binding material as cement paste, and then you have got stone aggregate, sand and so on. So that all gives you finally a composite, which is a useful material for specific application. You have got fiber reinforced composites. Many times we use those long fibers, very strong glass or carbon fibers, which are embedded in different matrix, different binding material, or many times you get powder reinforced composite also rather than fiber reinforced. Then you have got structural material which are there only for strength, like concrete, steel or fibers in fiber reinforced plastic. So they are there only for strength. There is no other application for that apart from providing the required strength. Then you have got aesthetic material which are there for looks only, for finishing purpose and so on, like your paint or cladding, stone cladding, or sometimes you use ACP cladding, those aluminum composite panels. So there are different types of materials, and then you have got these functional materials which are there only for specific objective. Like you must have seen the curing agents or the retarding agents used in concrete, where they delay the setting process. Otherwise there is no other function. Concrete will have its normal strength later on, but if you want to delay its setting process, sometimes you have to transport concrete over a distance and then you don't want it to set, so you use those retarders over there and so on. So there are functional materials which also you have to use for specific applications, or even corrosion resistance. So you want to use some materials to prevent the corrosion and so on, as a coating and so. Okay, so we say that we have various types of materials available for different applications, and depending upon our need we have to get used to those different characteristics and finally see which best suits our requirement. Now, having seen all these materials as a common man, it's only functional part we have seen, that it is used for this purpose or that purpose. But then as an engineer, when you design the structure, say you might use specific material, but which properties you will be interested in understanding whether that material is useful to you or not. So we say that we have got certain specific requirements from the material. I want to know its density because it will decide its self weight. I want to know its elastic modulus, so it will decide how much it is going to deform, the shear modulus or the bulk modulus. Then ultimate stress is required for that material, because that will enable me in designing the structure. You have got Poisson's ratio, so that we should know how much laterally it will deform if direction is one specific given to us. Then the percentage elongation, that also we want to know, because many times we don't want it to elongate too much in the given load and so. Then the yield stress and proof stress, that is also required, because many times that is used as a limiting value for designing the structural member. There is one ultimate stress, there is one yield stress, and then there is a permissible stress. So sometime it is related to ultimate stress, or sometime it is related to yield stress. Accordingly we will require that property also. Sometime you also are interested in knowing the coefficient of thermal expansion if you are dealing with hot gases, or a coating for hot gases, or your structure is exposed to high temperature gases and so on. Then you need to know its coefficient of thermal expansion and so on and so. Then the material properties, therefore, that we are generally interested, though we have seen the specific properties, we should know its strength, we should know its elasticity, its plasticity, whether it is going to undergo permanent deformations or not. In its hardness, sometimes it is required in industrial application where you want it to be scratch proof and so on. So you want to have a surface which is very hard, there will be no scratching on it. Or toughness, its ability to absorb energy. So these various properties are required in different applications. Its stiffness, its ductility, its ability to elongate and absorb energy. Sometimes it is required to understand whether it is a ductile material or not. In earthquake analysis particularly, we want the structure to survive in the worst of the earthquake. So at that time, it is not the elastic behavior that we expect in the worst of the earthquake, but it may undergo large deformation, permanent deformation, some cracking, but it will not collapse. So we want it to absorb a lot of energy before it collapses. So that will survive the structure and that will make it safe in the worst of the situation and so on. Likewise, you sometimes require impact resistant material if it is subjected to some impact load. Like in forging hammers, you must have seen those huge forces are applied for forging operations in mechanical applications, or fatigue type of loading where you are subjecting the structure to loads which are repetitive in nature. So like your machine which is rotating, so continuously there is up force, down force, horizontal, all types of forces are applied in quick succession. So that can sometimes reduce the life of the structure. So we say that the force may be very small, but it continuously changes its magnitude, its direction, and with that the structure gets damaged. It is not necessary for structure to get damaged when the load is very high. That is one aspect. But if for small load also, if it continuously keeps on changing, then that also has got adverse effect. Like you also, if someone gives you very simple task, or only do addition, nothing more than that, only 3-4 numbers you add, but there are thousands of such data and you keep on adding. So after some time, 2-3 hours, you will say that I have got fatigue, totally fatigue. Now I will not work. Let me rest. It was not a very difficult task. It was not manual task. You are not lifting 1000 kg or 100 kg, but you are still tired because of the fatigue that you have realized. Same thing done again and again. So that strains your system, and then we say that okay, that is fatigue. Same thing happens to material also, that if it is subjected to reversible load all along, and then you have got creep where sustained loading, same load applied continuously, then after some time structure start deforming. Initially it has deformed, but with the sustained loading it will have additional deformation. So in our day-to-day life also we also experience that for a long time you were under a lot of tension, and then at the end of the day you see that it has taken the toll. Now I am totally fed up because the same tension I have experienced for a long time, and then now your capacity to take additional load is now over. Now you say that okay, that is end of it. Okay, so that is what we say as creep, sustained loading. So it keeps on increasing the deformation, and in the end it may lead to failure of the structure also. Okay. So we say that structure has got important input required, that is in terms of material. So once we say there is a material, we have got a structural system which has got some loads to be applied, internal forces develop, some deformations are there, and now we have got to deal with materials. So we have seen various properties of the materials, but with all those properties, now my question still remains. I want to analyze the structure. So what is the use of all those properties which I have studied? I know the ultimate stress and I know coefficient of thermal expansion and all that, but is it all required for my analysis? So we see that okay, for analysis purpose I need to make some simple assumptions. So I make these simple assumptions. One, the material is isotropic, which means the properties are same in all direction. I might apply load in x direction or y direction or z, whatever it is. My properties, that is for example Young's modulus. Young's modulus is same in x direction, y direction, z direction. So that is what we say is isotropy. In each direction the properties are same. So that is my isotropic. So I make an assumption. A structure may be very large, okay, a huge shell structure is there, but I will say that at any point the properties in all directions are same. Okay, so that is what I say, it is isotropic. Secondly, I say it is homogeneous, which means everywhere, whether for beam support or mid span, anywhere, the property is same. I don't want it to have different properties at different places. Oh, that is very dangerous, because I will have to then each time see what is the property at that place where so much stress is there. So I cannot have my theory which can handle such type of situation. So I make an assumption that everywhere it is the same property. So we say it is isotropic and homogeneous. Homogeneity means everywhere it is same. Isotropic means at any point it is same in all directions. Okay. And thirdly, what we always consider as the material is linearly elastic. So we say that it is elastic, it is same property, but it is elastic also, which means if for some reason I increase the load 20%, my deformation will increase 20%. If it is 50%, like that. So it is linearly elastic. So my load deformation relationship or stress strain relationship is linear. So that is a guarantee to me that someone says, oh, I am applying this additional load. So we immediately see whether it is within elastic limit. Okay, that is fine. Then I can immediately calculate its deflection. So many times we do the same in our analysis. You increase the load, doesn't matter. Our E value is same. So our analysis immediately gives you proportionate increase in deformations and so on and so forth. So our assumptions made in structural analysis are, you have got isotropic material, properties same in all direction, homogeneous, everywhere it is the same, and lastly it is linear elastic. With that we start analyzing the structure, and then one important data is required, and that is the loads on the structure. So we say that the loads on the structure that we have are different types, and we have to deal with all those loads. These loads are to be anticipated by an engineer once he sees the structure, its application, the purpose for which it is built, what is expected, who are the users, and things like that. So all this information is gathered, and then finally with all that information you have got loads as an engineer would understand it. That is, you have got self-weight of the material or the structure as such, you have got imposed load in terms of floor finish or live load and so on, you have got wind load, externally applied load, you have got seismic load due to earthquake which may come once in a while, then you have got temperature load, either daily variation or yearly variation, or if it is industrial application then there is continuously exposure to high temperature and so on. Then you have got shrinkage and creep. So many times for concrete that becomes very important. So due to shrinkage some internal stresses are developed, you need to take account of that. You have got fatigue type of forces. So you have to see whether it is a very high speed machine, then you have to properly see whether your structure will have enough life for supporting that particular type of load. Then sometimes you have got lack of fit when you assemble all these parts like in a truss. So you take various members and join them. When you join them, many times you feel, oh, you have got this length, but when you exactly say it is 2.335, that is the length in meters. When you actually cut it, it will be 2.335 plus minus 2-3 millimeter here and there, because you can't get anything with exact length. Some tolerance you have to have. Tolerance may be in millimeters, or it may be in fraction of a millimeter, or sometime it is larger also. It all depends upon your fabrication accuracy. So once you have got a member which is either too long or too short in some way, but you have to anyway force fit it, because you can't throw the member up. It has to be finally assembled. So what you do is you force fit it, or you use a jack and stretch it, and then finally somehow put the member inside. So that lack of fit that we say develops some internal forces many times, and that you have not considered in your analysis. You have got a structure nicely assembled as shown in the diagram, subjected to loads, and your analysis starts. But here, when you assemble the structure, initially itself you have generated some internal forces, and you have no idea initially when you design the structure whether it will be lack of fit due to short length or due to long length, whatever it is. Accordingly, some internal forces will be always present. Then you have got pre-stress, with which you are all well versed with. So, for due to pre-stressing action, some internal forces are developed. Some buoyancy force sometimes you have to come across, you have to handle when you are considering structure floating in water and so. Or you have got pressure, maybe internal pressure, air pressure or liquid, or soil pressure when you are considering retaining wall and so on. Or in case of basement also you have to consider soil pressure. Then you have got electromagnetic forces when you are dealing with large electrical equipments like a transformer or a huge motor. Then apart from its weight and so on, or dynamic forces, there are magnetic forces also developed, and you have to many times provide for resisting such types of forces. Then you have got settlement of support. When you have the structure, you have done full analysis based on a firm support at the base. But as you apply the load, the soil is not a material with infinite stiffness, so it will undergo some settlement, small amount of settlement. Even when you consider bearing capacity of soil, so you say that it is so much bearing capacity, maybe 30 ton per square meter, with a settlement of 25 millimeter. So if that full pressure is there, it will settle by 25 millimeter. I mean, that is what we presume for defining the bearing capacity of soil. But what happens is, for some columns there is more load, for some column there is less load. But we say, oh, let us group them all and provide for all these 10 columns same size of footing, because every footing I will not change the size. Once you do the grouping, for some, at some place pressure is 30 ton per square meter, at some other place it is 20. So you say, oh, it is less than 35. But it creates another problem, that it settles differently. If it settles differently, it is safe as far as bearing capacity is concerned, but it is going to settle differently. To that extent, some internal forces may be developed. Many times they are not of great consequences, but sometimes if some excessive settlement occurs, then it can give rise to internal forces which can lead to collapse of the structure also. If some column settles due to some local weakness in the soil, then it can lead to very serious consequences. So we have to consider the analysis of the structure for all these types of behavior. Now we say that when you consider the analysis of the structure, the final objective is to design the structure safely. Okay. So we say that to design it safely means I want to understand in what way it will fail and then to prevent that. Okay. So we say that, okay, the structure can fail due to various reasons. Due to, we will say that the structure, finally I want to perform its function. So we say that for the function for which it is made, it must be able to perform that function. Okay, we will elaborate that. Then the structure must be maintenance free. So your structure should not lead to continuous maintenance. Every time some cracks are developed and you go on repairing it. So that should not happen. So we want it to be maintenance free as far as possible, at least for the initial period, maybe 10, 15, 20 years, there should be no problem. Or until, as a designer would casually say, until I do my professional career, I am in my profession, it should not give problem. Later on it will be that. Okay. So until my professional life, okay, it should be, but not that. A real engineer will always see that his structure outlives him. So it should be there for hundreds of years, but we will say that, okay, it should be maintenance free. It must have sufficient life, and it should be economically viable. You can't design a structure which becomes excessively costly and so on. So you want to economize on that, keeping the safety in mind, and of course it must be a structure which can be constructed also. If you involve technology which cannot be easily available there, sometimes it does happen. I mean, we have come across, I think Sandeep Swapnil knows it, that they designed a structure in New Bombay, that their head office. where they initially designed 40-meter span, the whole circular area, 40-meter diameter. They designed it in steel girders. Okay. Now each of the girder was weighing about 100 ton. There were 4-5 girders, and it was all within a huge complex. So a crane cannot just go there. So they had to put the crane outside and lift that girder, which is 100 ton in weight. So they realized after the design was complete, they ordered the steel and wanted to start fabrication. Then someone just asked that once you fabricate it, who the hell is going to lift it and put it at 25-meter height? So they realized, no, you need a huge crane. So they inquired all that, and they found that the crane has to be stationed outside the building, which is at least 50-meter away. 50-meter away, you so if you put the crane 50-meter away, it has to have a boom 50 meters and lift a load which is 100 ton and take it up. So they realized that no crane in the country has got that capacity. So after ordering the entire steel, they had to abandon the whole scheme. They had designed it, they had procured material, but in the end they realized that they cannot construct it because they didn't have crane to lift it up.
सर आता पिन वेगळी आहे का?
फ्लॅट तर माझ्याकडे आहे ते
चला लाईट येते
पुढे कळतं
सर असं एकच आहे एक पडलं वाटतं
इकडे राहिलं
हाँ नहीं ये इसका टूटा हुआ है स्क्रू पण लागेल आपल्याकडे असेल ना
सरांकडे आहे करून सर
हां परत सरांकडे चार्जर असेल
तुम्हाला प्रोजेक्ट करतात त्याच्यात एक आहे
डायरेक्ट लागेल का
तिथेच लाव
डायरेक्ट
त्याच्यातच लाव
लटकून देते
तिकडे
टू पिन वाला जाता टू पिन वाला है
So basically, once you plan a structure, you have to see that it can be constructed also. And another classic example is the Worley ceiling, which I think you all been there. So they had a huge central span, and they wanted to lift that whole girder up. It was 1600 ton girder, and it is in sea, so they needed a crane which is floating crane. So after fabrication and everything was completed, So after the fabrication was complete, they tried to search the crane available. So no crane in the country was strong enough and a floating crane. So 2 years they went on inquiring where it is available. So they found out one crane in America, Hercules was its name, Hercules. It was a floating crane. So they, after 2 years, they brought the ship there, and then it was lifted and put there. Otherwise, they were just worried. I mean, they were just confident we will do it, but didn't plan it. And then finally, you have to see that the construction is possible for whatever design that you are finally doing it. You can't say it is not my problem, because if the structure cannot be built, then it is everybody's problem. So we say that if at all I want to design the structure properly, then we have to anticipate in what way it is going to fail and then prevent that. Okay. So we say that firstly it can fail by overstressing. So I want to select a material which is strong enough, calculate actual stress, see that it is less than permissible, then fine. Then I want to prevent its failure due to buckling, and under compressive load it should not buckle. Failure due to creep, I want to limit the stress so that due to creep no excessive deformation occurs. Failure due to shrinkage, many times you see those roads develop lot of shrinkage cracks. So that is a kind of failure, and we want to avoid that failure due to shrinkage. Failure due to fatigue, again due to that machinery load that you are considering. Failure due to settlement of foundation. So I want to limit the settlement so that excessive stresses are not developed. Failure due to unforeseen or accidental situation. Many times you have to see the undue risk is not required to be taken. Otherwise it can also lead to failure. In normal circumstances things are better, but when you take risk in your normal activity and see that, oh no, I have done it many times, let me take the risk, then it can also lead to failure. And then failure due to excessive deformation. Many times the structure deforms too much, and then though an engineer might say, no, stress wise it is fine, don't worry, but the user will say that no, it has already tilted, so I don't want to occupy it. Engineer will be confident that stress wise it is fine, but user must also finally feel that it is a safe structure. Okay. So we say that the structure must perform the intended function, and the safety must be ensured when you design the structure, and so on. While now we are almost coming to the end of the presentation, that for analysis of the structure we have got standard tools which are there for you right from your college days. You have seen these standard tools of analysis. One was the equation of equilibrium. So you have to see that all the applied load and internal forces are in equilibrium. Then you have got compatibility condition, which means we say that now these are our normal equilibrium equations, sigma fx equal to 0, fy and so on, normal for three-dimensional structure. Then your compatibility condition means structure must deform in such a way that all members remain connected, no member gets dislodged, and it is a continuous structure all along. So that is what we say, the compatibility condition must be satisfied. And lastly we say that the Hooke's law or the linear elasticity must be ensured. So your stresses must be such that the elastic limit is not crossed, and on unloading the structure you should get the original undeformed structure, and so. So we say that the structure must be designed so that Hooke's law is applicable all along. So it is a linearly elastic behavior under which we are doing the analysis. And we have got these three methods, out of which the first one is the only one used in the current industrial applications. The stiffness method, which we shall see later on. The flexibility method, which sometimes is used in college days, it was very popular method, but in industry or in real life no one uses that. And mixed method, that partly it is flexibility and partly it is stiffness. That also only researchers might use it. or for very specific applications people use the mix method and so we can say that as far as the basic analysis tools are concerned, we have got only one method to be dealt with, that is our stiffness method. So we shall be using stiffness method in our analysis and see how we determine the internal forces, which I have indicated to you, only 4 types of internal forces, and stresses to be determined later on. And finally we say that we have to design the structure in such a way that the actual stress is less than the permissible stress. Failure of all anticipated types are avoided. I think with this we come to the conclusion of today's presentation and see that we shall continue with our next step next time, when we now consider the next step in the analysis, which I have indicated, that we have to determine the stresses in the given material, that our design process would require stresses. So we shall see how the internal forces, once you determine in your analysis, how they are converted into stresses, and then compare with the property of the material that you are handling. I think with this we shall come to the conclusion. Okay, thank you very much for your patient hearing.
नेक्स्ट टाइमसाठी तर यांना काही द्यायचं आहे का असाइनमेंट वगैरे असं काय?
त्यांना आहे का, म्हणजे मला असं वाटतंय त्यांना द्यावी असाइनमेंट.
हां हां
मग मी असं करतो, एक क्वेश्चन आजच तुम्हाला मेलवर पाठवतो,
ठीक आहे.
म्हणजे मग त्यांना मी जे जे काही शिकवलं तर त्याच्यातलं त्यांना जे जे